up for Derek.
Hey. Thank you, JP. Of course, I have to thank you, JP. Thank you, Lyft, for having us here. I am super grateful to be up on this stage and talking to you all tonight. And I'm watching Greg take pictures of me. So I'm excited to be here. Thank you all. I got to ask, show of hands, who knows what class dump is? That is probably like 90%. It's pretty good. Class dump is this kind of, it's almost a 20-year-old tool. I had to research it for the whole talk. I made this super small, so it's hard to see, but even Apple knows about this lovely tool. So it's a tool that will dump your compiled Objective-C code and make it into, it could pretty much rebuild the header to Objective-C code. So let me read this super small thing. We have a UI view controller category which says, class dump warning, attention class dump user, yes, it's us again. Although swizzling and overriding private methods is fun, it wasn't much fun when your apps stopped working. Please refrain from doing it in the future. Okay, thanks, bye. So that method, I think, was around in 2009. So this tool has been around for quite a bit. So I thought, hey, why not give a talk about it now? Because there's a lot of different stuff out in the wild. So have to go through it just so you can visually see. I know this is the slug meetup, but I do have to show Objective-C before I build up on Swift. We have our very basic Objective-C code. We have our, actually, show of hands too, just so I know how fast or slow to go. How many of you have done Objective-C before? Okay, all right, so we're good. I can breeze through this stuff. Okay, so compile this, clang, temp, main, need the F modules to bring in the foundation and all that. And going back to hardcore C mode, we have our a.out. If we don't specify the out file. And then running class dump on this executable will get me the methods for Objective-C. So let's talk about class dump with Swift. I have a very simple Swift file. Example1.swift just has a class. That's it, with one function called instance func. Compile it. Run class dump on it. For this case, I'm saying grep for everything that doesn't include a comment in it, so not. And so we can see some kind of weird stuff here. It's got this weirdish mangled name. It inherits with the Swift object, still kind of weird. We don't have that instance func that was declared in that class. So something's kind of weird. It's like there's, there seems to be Objective-C in this, but it's Swift, and it's definitely not picking up the function that was declared in that class. Another problem. The latest and greatest, ARM64E on your iPhone XS and above. And soon to be probably your Mac computers in probably like 2 or 3 years or whatever. Have your file, example1.swift. Compile it, but this time compile it for the iPhone SDK. I'm just giving it a bogus bogus triple, sorry. Of 99.99.99.99. Compile it for ARM64E. Let's see what happens. Class dump, unknown opcode. What the hell? So this is getting into the dynamic libraries, or DYLD's opcodes. This is complicated. I only have 30 minutes to talk about this, but I'll try and kind of breeze over it when I'm going through everything. There's a lot to talk about for this stuff. But it is possible to do this. Whoops. So this is a tool I wrote just for whatever, because I'm masochistic. It's called ds-dump. I'm saying dump the Swift code, make it super verbose, so I add all these cute reflection helper comments, print in color. So you can print this out. This is all included in your executable when you compile it. So if you were to pull this from the App Store, just talking about this because you probably think, or just so it applies to you. Once you go through Apple, goes through the App Store, Apple will encrypt a certain portion of your executable. I'm going to talk about that portion in the mach-o segments in a second. But if you were to decrypt it, this is all viewable in your app. That's compiled in Swift 5.1 right now. So all you need to know for this talk, which I'm going to just kind of half-ass all these concepts, but just to kind of give you an overview of them, is mach-o, my favorite, and I apologize to both of you because you have to sit through me doing this, talking about this yet again, so sorry. The symbol table. And let me actually back up. Looks like all of you know your Objective-C. Remember the headers. I'll show you a quick command just so you can view them in terminal in a second. So, but I'm just showing you the headers that kind of relate to the concepts I will be talking about. So mach-o, check out this header. The symbol table, check out this header. Check out this tool. If you're not on Slack or Twitter right now on your computer, you could man that or man that. Let me back up. The symbol table is useful for declaring and declaring what symbols are needed externally. So let's say you're class dumping something and you have an object that is referenced as the parent class in a different framework or module or dynamic library or whatever. You need the symbol table to declare that, hey, I need that class in this framework. I'm going to kind of group these together, at least for class dumping, but they're very different. The DYLD opcodes, they are the implementer to external references outside in different frameworks. So these binding opcodes, once your executable loads into memory, these opcodes will go through and bind certain virtual memory addresses in your code. And I won't go too deep into this because this is kind of boring stuff unless you're writing your own, but I'll show you the high level of what's happening. And then, of course, Objective-C, because all Swift classes inherit from Objective-C. And, of course, Swift. And JP, I am horrible at time management, so if like 5 minutes out, just start yelling at me, because I'm going to jump to a certain section just to make sure I got everything I want to. So yeah, just yell at me, because I'll just be in my own little zone, because I'm about to just go off into terminal right now. So here we go. Demo time. Yay! All right. Yay! I'm not done. I'm not done. Okay. Alrighty. Let me sit down and get comfortable. There we go. All right. You can still hear me all right? Great. Okay, so what did I say first? I said let's talk about the mach-o first, and let's talk about the header. So a second ago I said it was in mach-o/loader. So to look at that, to hunt that down on your terminal, you could do xc run show SDK path. And then from there, I'll just copy that. Boop, boop, boom. User include mach-o loader. Boop. So that's this file, which I'm going to show you right here in Xcode, just because it has pretty color, syntax, highlighting, I'll stick with that. So I'm sorry again, I could do this. I'm gonna start with the same thing. Whenever I talk about mach-o to people, I always go with the same kind of motions, and just to show how approachable it is for everyone. So I'm gonna do this. I'm gonna type in xxd, group the bytes into 4, sort in Little Indian order. Someone gave me a terminal command. It can literally be anything, except, well, if it's a shell script command, then I'll be like, don't do that, but you probably won't get one. Who am I? Okay. All right. Once again, group the bytes into 4. Put in Little Indian sorting, because there's Big Indian and Little Indian. On an x86 64-bit Intel architecture, it's Little Indian. Only print out the first 2 lines, head 2. Now, right at the start, the very beginning of almost every executable doesn't apply to JavaScript, doesn't apply to not compiled code, but there's going to be this header, this magic number called feedfact. And we can cross-reference this to this struct right here. So this is the magic value that will say, hey, this is the start of the mock header 64. Right into here, the CPU type, cross-referencing with this. Jumping to this value, we have that, this is all in hex, 01000007. Jumped into that, and looking into the header file, we could see CPU arch ABI 64. We can see it's ORed right here with CPU type x86. So these 2 values are ORed together. This is telling me that this is compiled for an x86 64-bit machine. Right? So if you compiled it for ARM or something, you'll get a different value here. Subtype, same dance, I'll skip that. File type, we have a 2 here. So let's look at that. File type, let's search for, what is it? mh-execute. Demand page executable file. So I know this is an executable. It's going to run by itself. It's not going to need any help with like a framework, or it's not a framework. What do we got here? Dynamic library, that'd be a 6. Okay. Now here's the important part, and here's the part where I'm going to cut off, and then I'll finally get to something new and exciting. It's the number of commands. These load commands are kind of like the table of contents to an executable. They say what virtual memory goes where, and what gets loaded, all the frameworks that is needed. It's like all the, it'll provide the location for the symbol table, which we'll talk about in a second. So this is interesting, and this kind of guides what I will be talking about in the exciting part that should be coming, hopefully. All right, so I can see here it's 10. Again, that's hex, so it'll be 16 in decimal, right? So if I were to look at this in a different way, I'll do change to boop. So I'm going to switch to O-tool now, and O-tool has a command to inspect the mach-o header. We're going to look at that. We can see the number of commands match here, right? 16, 10 in hex. CPU type, that'll match here. This is in decimal, but that will match for hex. Okay. So again, the part I'm trying to get us to is going to be the load commands, and so let's dump those right now. Using O-tool, -L, this will dump all the load commands, and there's quite a bit, so I'm going to make it bigger. Any of you run this command before? Nice, okay. The Apple developer. So these are the commands that dictate what gets loaded where. These are important to a program. So this is one way to view them. I'm going to switch it up and use a tool that you likely do not have on your machine to make it a little easier to view. So I'm going to use a tool called JE tool from kind of a security person I highly respect. Okay. Back up here. Two more concepts and we'll get into other stuff. In memory, you have in mach-o. That sucks. The phone's okay though, right? Cool. Okay. Okay, so you have a big area of memory called a segment. This segment is going to have all the same memory permissions. In that segment, you're going to have these little subsections, subcomponents called mach-o sections. This is a segment. It has 0 sections. This is the area in memory that if you dereference a nil pointer, or if you do the implicitly unwrapped and you have a nil value, it's going to hit here. This part does not have readable, does not have writable, does not have executable. This is why your program crashes when you do that, when you're dereferencing a nil pointer, because you can't read this memory, you can't do anything with this memory. This is done on purpose, so you don't screw up pointer arithmetic. Next segment is the text. This is readable and executable. So all your compiled code goes right here, usually, unless people are trying to do crazy stuff to you. We have all these sections here. I'm not going to go into them, but this is totally a talk in itself, and there's a lot of cool things in here. But we're going to go, sorry, let me undo that. Here's the next segment. This is data. This has readable and writable. So your code, any variables that you set, like global stuff, that gets stuck into here. This is important because Objective-C sticks a lot of code into this segment. And therefore, it's important to Swift because any class in Swift is inherently Objective-C. And we'll talk about that if I have enough time. Okay, so let's go. So that's kind of the quick mach-o overview. Again, kind of doing a meh job, but just so I can just get you interested in knowing what's possible. I'll now jump to the symbol table. So I'll just compile a very quick thing. We'll do Swift. Okay, example Swift class. Yay. And then we'll do, I don't know, func test. Nice and easy. And print. Yay. Yay. I got it, I swear. Swift, C, example, Swift. Okay. So let's look at the symbols that Swift has in the compiled executable. Isn't that crazy? Something so simple like that, it needs to reference a bunch of internally defined things done by the compiler, and then a bunch of externally defined things that it needs to reference from other libraries. So I think U is going to be the internal. Lowercase u is the external, right? So just something simple in the compiled code, it needs to reference Objective-C get class. And so this is very important to kind of how a Swift or Objective-C class references other classes outside of itself. Okay? So then jumping again, actually, how much time do we have? So I have 15 minutes or so? Question mark? Okay. All right. I will just go straight to Objective-C. I kind of want to show you all this stuff. It might not be like, not totally pertaining to Swift right at first glance, but it all builds on top. And so there's a lot of C, Objective-C code that's built underneath for you to appreciate the Swift reflection metadata. Okay, so Before doing Objective-C, I just want to quickly talk about your Agnes's blog. No, this is good. This is I'm going to reference this to, because now it'll get a little more exciting in a second. Okay. Agnes here wrote a great link on, hunting down a bug, and in it, she talks about the Objective-C runtime. And so, scrolling down, there's a discussion on what is a class. From the open source runtime code, this is Apple's published code for Objective-C. Okay? In this published code, we have a struct Objective-C class. Actually, let me show you something kind of cool. If you've ever been to opensource.apple.com? Yes? Okay, great. So you have all these funky numbers, right? So let's talk about how they get those numbers for these links. Let's go to terminal. Oops, terminal. I'm gonna look up the compiled dynamic library that Agnes was just referencing. So let's go to cd user lib Objective-C. I think that's just a symlink for one of them, but we'll just go after you. Okay. Oops. So what I'm doing is I'm trying to explain the links, why those links are kind of weird, and how does Apple figure those links out. It's this compiled source version in the mach-o load command, right? So I can see the source version is 756.2. If I were to go to the links here, we can see that this is the source code for the compiled executable on my machine. And it kind of depends on code base to code base, but sometimes what you have on your computer will be a little bit farther ahead than what Apple will externally publish, just because legal reasons and stuff that's above my head on why. So with that, let's talk about Objective-C. I'm just going to compile a executable here. Command. I'll add some Swift code to this in a second. All right, just build a really quick class. Interface, yay, NS object, the fun stuff. And good. Okay. So Objective-C and with the mach-o sections, you really can inspect them quite well, both on disk and in memory. So I'm going to do the sections. I'm going to display the sections using a custom LLDB command yet again. This is displaying right now. This is kind of a little confusing, but if you don't have anything, I'll display all these segments first. If you add in a segment, I'll display the sections. Okay. And since I'm not referencing it, I need to do implementation, yay, and I'll do some function here. Do stuff. There we go. Now it'll get compiled in, hopefully. There we go. Class list. This is how people inspect binaries. This is how class dump really works. You're looking for a certain sections in the data segment. This will point to the Objective-C data payload. And this is actually how you can figure out how many classes are implemented in a certain executable or dynamic library. You divide this value here, the size, by the size of a pointer. So I can tell that there is one Objective-C class implemented in this executable. You can dereference this. So it's a pointer to Objective-C class, and if I were to print this, I should get yay. Okay, so that's that's pretty much kind of the Objective-C stuff. Now, if we look at 750, I'm gonna finish up Objective-C and do the cool Swift part in 3 minutes. Okay. Runtime, or I'll use Agnes's link for that. Can you see that all right? Sorry, I need to find the code for the class. So what makes up an Objective-C class, which is the base for every Swift class? It inherits from something called Objective-C object. This implements the ISA. After that is the superclass. So if we were to dump this raw memory, let's just dump all this stuff. This gets complicated because they pack bits into their pointer. A pointer should be 8-byte aligned. It's 9 right now, but I won't get into that. That's crazy. The superclass should be right here, right? It's hard to see, but the ISA is at offset 0. The superclass is at offset 8. Let's confirm this. This should be an NS object, right? Okay. This address at 8, this is what the DYLD opcodes do. They bind the external addresses together. And let me try and, yeah, I'll do that in 1 minute. Okay, so another custom LLDB command. This will execute into terminal mode. I'm going to do a custom, this is in my little command that I made for debugging purposes. So I'm going to run, sorry, what do I want to do? It's OPCS for opcodes, there you go. Print it, or apply it to the executable, grep for this value here. Now what I'm looking for is NS object being bound to this address. So this is what the DLD opcodes are doing, right? And we could see that. So this is what happens when stuff gets loaded into memory. Before you even touch any code, this is what happens for the binding. Now let's talk about Swift in 7 minutes. Now, what Apple does is, don't need it, is they do something kind of sneaky for the mach-o sections, and I'll show you that right now. So we'll do class, a Swift class. We'll do the boring yo, 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 yo. Let's examine the mach-o sections again. I'm going to go after a section inside the text segment. We can see these lovely Swift 5 type ref field MD types. These are kind of took me a second to figure out because I was not smart enough to read the source code, but just actually jumping through memory. So what they do is they have an address and they have the value at this address. And this value is a 32-bit int. They take that 32-bit int and they apply it to the address, and that will give me the offset to the Swift reflection data. That sounds really crazy and it sounds like my head's going to explode, but let me just show you and I'll step through it just to show you what I'm doing for a class dump. So I'm going to take this value here. I'm going to say, hey, print, dereference this in the size of a word. If you're into C, which probably most people aren't, a word is going to be the size of 4 bytes. That's going to be an int in a 64-bit program. I'm going to print it out in decimal. I have this value negative, important, negative 108. So I'm going to add this value. or add it, subtract it. And this will give me the reflection metadata that I am looking for in Swift. So if I were to query what this address is, it's a nominal type descriptor. And this is kind of, if you go to Swift, the GitHub repo, and you go to like Swift include metadata.h, that is the class that's responsible for the layout of all these structures. So this one person, reverse engineer dude, I think, let me see what he did. Swift metadata. He wrote a nice little blog post that details all the layouts, because this is in C++, and it's always hard to follow the offsets to your to these memory addresses with some very complicated classes. So he just dumps them all out, and you can see that the we'll do class descriptor struct. So at offset uint32 has these flags. At offset 4, we have the parent. At offset 8, we have the name. So I will print out the name, and then I'll call it a day for questions. We have the value here. I'm going to do print out 3 word size values. That's an int 32. Print out in decimal. So this value here, minus 20, should hopefully give me the value of whatever I called the class, which I forgot, a Swift class. So x minus s minus 20, and I'll put those in backticks. So LLDB tip is if you use backticks, it will compile that before actually executing the code. And that'll give me the Swift class. And so this gets really complicated because there's all these crazy structs that are embedded in here. And again, if you're curious about this, go to Swift GitHub repo, go to metadata.h, and just read through that header file about 20 times to really get a feeling for it, because it's complicated. They did a really crazy job, and they're still continuing to do crazy jobs on trying to optimize every little bite of this stuff. It's really cool to see it kind of evolve over time. So I hope I didn't scare you too much. That's kind of the high-level overview of some concepts that I should be spending hours and hours and hours on. But hopefully that just to show you what's possible, to show you that you can inspect your own app that's compiled, even when it's stripped out. You could still look at a lot of information that's still available, even if you strip this code out in Swift, unlike in Objective-C. So I think that's it. Thank you.
All right, we'll do one quick question, and then we'll jump to our second talk. And if you have more questions for Derek, you can talk to him after both talks are done. So please just raise your hand if you have a question. We'll take one. All right.
I'm just kind of curious, when I read the description of your talk on the site, it mentioned something about this is something that pirates or people who want to reverse engineer your code can use. So with these tools, what can they expose that could be compromising to your app? Like anything, if at all.
It's not as bad, maybe I did fear mongering, but it's mainly the names. And with the names, once I have names of functions, I can get a really good overview on what I want to explore or not. And even with Swift will let you strip out some of the names of the functions, even the classes, but I still can get that metadata information on, hey, this is a getter or setter. So I just ignore those functions, and I can focus on the important things. I think if you're hardcore, there's Hopper, which is kind of the easy bake reverse engineering tool. Going a little bit more hardcore, there's Ghidra from the NSA. There's also IDA. So you could write a pretty powerful script to kind of quickly filter out all the kind of the noise of Swift to get to the really good stuff, which you know, you still need a disassembly tool to kind of you know, unpack all that, and then you know, got to be good at the ARM and what will eventually be ARM-E for pretty much everything in the future. But yeah.
Oh yeah, it gives them a start, an overview
Yes.
of what's in your app.
Yeah.
Yeah, because one of the things I'm concerned about is obfuscating, and also if you're using encryption, like for the Realm database, you know, you want to do something tricky where you assemble that key from different sources and then maybe feed that in, but then they can just go right to that function and see what is going in there, and then they've got your key, right? So, you know,
Yeah, it's
if you're not putting it in keychain.
yeah, it's if the phone is jailbroken, it's pretty much game over, no matter what you do. So, you know, this is not the best answer, but if you're totally paranoid about, you know, security and all that, just do the latest iOS. But that's not going to be the realistic thing for pretty much any of us in this room. But that's my only recommendation I could say for, you know, to be totally secure. So it's always a cat and mouse game.
Okay, thanks again, Derek.